So, I have an easy energy example for you to get started with how to solve work energy problems. So the problem reads, a heavy 17,000 kilogram airplane lands with a speed of 82 meters per second on a stationary aircraft carrier deck that's 115 meters long. The plane stops in the whole distance. Find the work done in stopping the plane. Okay. So what's our picture going to be? Well, we've got a plane. How do you draw a plane? Okay, so we start with it moving, and then 115 meters later, it has come to a stop. This is 115 meters. What else do we know? We know the mass is 17,000 kilograms. It's going to have a lot of energy. Oh, sorry, Kat. Initial speed is 82 meters per second. Okay, so this is my initial speed. The length of the deck is 115 meters. And we want to know, what is the work done in stopping the plane? Okay. What is the work done in stopping the plane? Got my picture? And I'm going to say this is my initial place. This is my final place. And then I'm going to jump right into my energy equation. Initial energy plus minus work equals final energy. Okay, what kind of energy do I have to start with? The three questions we always ask, is something moving to start with? Definitely. So we have initial kinetic energy. Is something above its lowest point? Well, okay, let's define an origin. I'm going to say this is my origin. That just seems to make a lot of sense. Is something above its lowest point? No, doesn't change height. Okay, so no potential due to gravity. Is there spring? No spring. No spring energy. So my initial energy, in this case, just kinetic. Final energy. Is something moving in the final situation? Nope. Is it above its lowest height? No. And then is there spring? No. So what do I put here? Well, there is no energy. We're just going to put 0. So if we start with something and we end with 0, we know there must be negative work done. And that work is done to stop the plane. So it's moving, we do some work to slow it down to a stop where it has no more energy at all. We want to know what that is. So this doesn't look too bad. Kinetic energy is just going to equal the work done in stopping the plane. 1/2 mv initial squared equals the work. And let's see, 1/2 mass, 17,000. These are big numbers. Speed is 82 squared. That's actually one of the real common mistakes, is to forget that squared. So just keep that in mind. If you do the math, you get a very, very, very large number. You get 5.7 times 10 to the what? 7 joules? Holy smokes. Because that's how much energy the plane, when it was here, it had this much energy in kinetic energy. And that's what we had to do. We had to pull away all that energy to bring it to a stop. We took away all its energy. Now, one of the cool things about work energy problems is now we know the work done, and we know that the work is the parallel force times the distance. I know the distance. I can get the force that it took to stop the plane. So the parallel force is going to be the work divided by the distance. So 5.7 times 10 to the 7 divided by 115 meters will get you about 5 times 10 to the 5th newtons. That's a lot of force. That's a lot of force. And what's doing that? Mostly friction. You know, you've probably got a tail hook and stuff like that. But you know, we could say that's mostly friction there. So that's just a real simple problem on energy, just to get you start thinking about how to use this equation, what we call the conservation of energy equation, to come up with this. And once you have that, then you can just keep doing it and figure out all of that stuff. All right, good job.